Now we will see single tone modulation of AM. So here we are considering one example. So till now we have not taken any message signal. In general, we have discussed the frequency spectrum. Now by taking an example of single sinusoid, so here by considering modulating wave as AM cos 2 pi FMT. So it is called single tone modulation because this is having only single frequency component. So now the AM wave is described by this equation, AC into 1 plus Ka m of t. So m of t is replaced by this quantity AM cos 2 pi FMT. So now if we represent this as shown here, AC into 1 plus mu. So this Ka into AM is represented by mu, which is known as modulation factor. So this will be the AM wave for single tone modulation. So as we have discussed earlier, to avoid the envelope distortion, this Ka AM value should be less than 1. That means the modulation factor mu should always be kept below 1. And let us assume that A max and A minimum be the maximum and minimum values of this envelope. So if A maximum is the maximum value and A minimum is the minimum value, so in order to find the maximum value, we can replace this cos function by its maximum value, which is plus 1. So the maximum value becomes AC into 1 plus mu. Similarly, to find the minimum value, replace this cos function by minus 1. So the minimum value will be AC into 1 minus mu. So if we consider the ratio A max by A minimum, so it will be AC into 1 plus mu by AC into 1 minus mu. Since here the cos function maximum value is plus 1 and here the minimum value of cos function is minus 1. So this will be the ratio of A max by A minimum. So now if we simplify this by taking A max minus A min by A max plus A min, so we'll get 2 mu by 2, which is equal to mu. So from this we'll get the modulation factor as A max minus A min by A max plus A min. So now considering this time domain equation of single tone modulation and simplifying it further, so we will get this first term as AC into cos 2 pi FCT, and the second term will be AC into mu into cos 2 pi FMT into cos 2 pi FCT. So now by using the relation cos A into cos B is equal to 1 by 2 times cos A plus B plus cos A minus B. So by using this relation over here, so we can simplify this further as, so this first term will remain as it is, and the second term becomes AC mu by 2 cos A plus B. That means the sum of these two frequencies, 2 pi into FC plus FM, and the second term will be A minus B, that is difference of these frequencies. It is cos 2 pi FC minus FM. So we are taking FC minus FM because FC is always greater than FM. So this will be the simplified time domain equation of single tone modulation. So again, in order to plot the frequency domain description, so by taking Fourier transform of this equation, we'll get this equation. So again, as we know, the Fourier transform of cos function is expressed in delta. So this will be AC by 2 del of f minus fc plus del of f plus fc. So coming to the second term, so it will be AC mu by 2. Already 1 by 2 is there. So again, if we take 1 by 2 times del of function, so it will become AC mu by 4. So since here the frequency is fc plus fm, so here the delta function will be shifted by fc plus fm on both the sides. And similarly, for the third term, the frequency will be fc minus fm. So hence the spectrum of this AM wave will have, which is special case of sinusoidal modulation, it will have delta functions at plus or minus fc, fc plus or minus fm, and minus fc plus or minus fm. So if we plot them, so here instead of general message signal, we are taking a cosine signal of frequency FM. So for a cos signal, if we present it in frequency domain, so it will be having two delta functions, one at plus FM and other one at minus FM. So similarly for the carrier signal, so it will be having two delta functions at plus FC and minus FC. So for the modulated signal, so we'll be having these frequency terms. The first one are the frequency components of plus or minus FC, and then the same message spectrum shifted in frequency by FC. So when this spectrum is shifted to the right by quantity FC, so this spectrum will be plotted over here. So this will be, so since it is being shifted to the right by FC, so it will be centered at FC, and this upper limit will become FC plus FM, and this lower limit becomes FC minus FM. And coming to the last fourth term, so again the same spectrum is shifted to the left. So this will be centered at minus FC, and the upper limit becomes minus FC plus FM, and the lower limit becomes minus FC minus FM. So again here the bandwidth of SS signal is FM, and the bandwidth of this modulated signal becomes 2 times FM. So this is the special case where we are considering a single sinusoid as the message signal. Power calculations in AM wave. So this is the AM equation for single tone modulation. So this part is the carrier, this is the upper sideband, and this is the lower sideband. So in order to calculate the power required for AM wave, so first let us see how we can calculate the power value. Power is given by V RMS V RMS into I RMS, or we can also write it as V RMS square by R. So for simplicity, we will be taking R equal to 1. So the power value will be V RMS square. And we know the relation between the RMS value and peak value. So this becomes V peak by square root 2 whole square by 1. So the power value will be V peak square by 2. So power in every, so we have to calculate the power for each of these terms. So power can be calculated by using V peak square by 2. So if we observe the first term, so in order to calculate the carrier power, so the power of carrier will become P C equal to, so Vp square by 2. Here maximum peak amplitude is AC. So the power of carrier becomes AC square by 2. So this is the power of carrier wave, and this part represents the upper side band because it is centered at frequency Fc plus Fm. So in order to calculate the power of upper side band, so this is the peak amplitude 1 by 2 AC mu. So the power of so upper sideband is represented as USB upper sideband. So this power will be AC mu by 2 whole square by 2. So it will be equal to AC square AC square mu square upon this 2 square is 4 into 2, so it will be 8. So AC square mu square by 8. So similarly, if we calculate the power of lower sideband, that is this frequency Fc minus f1, here also the peak value is 1 by 2 AC mu. So both these values are same, upper sideband and lower sideband. So the power of lower sideband will also be equal to AC square mu square by 8. So now if we represent this power of upper sideband in terms of carrier power. So since it is AC square mu square by 2 into 4, we can write it as. So we know that this AC square by 2 is nothing but power of carrier. So we can represent it as PC into mu square by 4, which is also equal to power of lower sideband. So if we represent this power of upper sideband and lower sideband in terms of power of carrier power, it will be equal to PC mu square by 4. So now the total power required to transmit AM wave will become ET is equal to power of carrier plus power of upper sideband plus power of lower sideband. So which can be written as PC plus PC mu square by 4 plus again power of lower sideband is also P PC mu square by 4. So if we take PC common, it will be 1 plus mu square by 4, and mu square by 4 becomes 2 mu square by 4, which is equal to mu square upon 2. So the total power required to transmit AM waveform can be given as PC into 1 plus mu square by 2. So the same thing I have written in the slide. So power can be given as VRMS into IRMS or VRMS squared by R. You know that the relation between VRMS and peak voltage is given by VRMS equal to VT by square root 2. So by taking R equal to 1, we can find the power by using VT squared by 2. So for calculating the power of carrier, it will be AC square by 2, and for upper sideband it will be AC mu by 2 whole square by 2, which will be equal to PC mu square by 4. Similarly, the lower sideband power. So now the total power becomes power of carrier plus power of upper sideband plus power of lower sideband, which will be equal to PC into 1 plus mu square upon. So this is the power of total power required to transmit an AM wave. So now there is one parameter called transmission efficiency. Is that how much efficiently we are using the transmitted power. So it is defined as total sideband power divided by total transmitted power. So total sideband power is nothing but power of lower sideband plus power of upper sideband. So it will be equal to PC mu square by 4 plus PC mu square by 4, which will be 2 times PC mu square by 4. So the total sideband power will be PC mu square by 2, and the total transmitted power is PC into 1 plus mu square by 2. So cancelling these PC values out and simplifying it, the transmission efficiency will be equal to mu square upon 2 plus mu square. So now let us consider an example. Let the total power required to transmit AM wave is 300 watts, and we are taking modulation index value mu as 1. So by substituting these values over here in this equation, PT equal to PC into 1 plus mu square by 2. So 300 equal to PC into 1 plus mu value is 1. So it will be equal to 3 by 2 PC. So from this, as 300 equal to 3 by 2 PC, the power of carrier will become 200 watts. And the power required to transmit the sidebands will be obviously equal to the total power minus carrier power, which will be 100 watts. So if we observe here, out of 300 watts, 200 watts of power is required to transmit the carrier, and only 100 watts is being used to transmit the sidebands. So we know that the information is present only in the upper sideband and lower sideband. So if we observe the figure here, so that message signal is present only in the upper sideband and lower sideband, but there is no information present in the carrier waveform. We know that the carrier is only used to transmit or carry the message signal for longer distances, but the actual message is only present in the sideband. So here we can see that out of the total transmitted power, 200 watts is being consumed by the carrier, and only 100 watts is being used for transmitting the message signal. So 200 watts of power is wasted to transmit the carrier. That is, 2/3 of the power is lost in transmitting the carrier, and only 1/3 of the power is used to transmit the sidebands. So this is one of the disadvantage of standard AM modulation. So we can call it, we can also call it as double sideband with carrier, because we are transmitting both the sidebands and carrier in this standard waveform. So it can be called as double sideband with carrier. So that is the reason why we go for other types of AM modulation like double sideband suppressed carrier. That means we will be removing the carrier and we will be only transmitting the double, both the sidebands. So that is the reason why we are going to DSBSC, which we will be studying in the next lectures. So in order to increase the transmission efficiency, so for the standard AM wave, the transmission efficiency is very less. So if we take mu equal to 1, the transmission efficiency is 1 by 3. That means we are only using 1/3 of the total power to transmit the message signal. So in order to increase this transmission efficiency, we go for double sideband suppressed carrier technique.